section 3 of Principles of Flight, and in this section we're going to look at the forces in flight, what we mean by equilibrium, the glide angle, how the center of pressure moves as we change the angle of attack, the inherent instability of a wing, and the purpose of a tailplane. First, we'll visit Newton's first law, and he states a body at rest or moving at a steady speed has the forces acting on it in equilibrium. And this can be shown here fairly simply with this diagram. We have a weight on a flat plane, and its weight is acting downwards towards the center of the earth. And in response, the surface itself is pushing back up, if you like, and the net result is the object doesn't move, it's stationary. And this is considered to be in equilibrium. A glider in flight is in equilibrium if it's not accelerating or decelerating, and most of our examples when we're looking at the principles of flight will be considering it as in equilibrium. The top diagram is showing us what you've seen before, and that is the total reaction acting upwards and the weight acting downwards. The object isn't accelerating or decelerating, and you'll notice that there isn't a component in there showing the direction of flight, even though the object is moving in flight at a steady speed. We can take the total reaction and subdivide that or resolve that into two component parts, lift and drag, and we've seen that before. And that's been done on the lower diagram here. So lift now acting at an angle upwards and drag acting at 90 degrees to the left. And that's shown here. So we have lift acting at 90 degrees to the relative airflow, weight acting vertically down towards the center of the earth, drag acting in the opposite direction to the relative airflow and at 90 degrees to the left, and the flight path, which is the route that the glider is taking through the air, and you'll notice that that is a slight downward slope. When we talk about glide ratio, we're talking about the ratio between the lifting force and the drag. And a typical glide ratio for some of the earlier gliders might be something like 30 to 1. And what that means is the glider will travel 30 units horizontally, so perhaps 30 feet horizontally, and in that time descend by 1 foot, so 30 feet to 1 foot. And from that we can calculate the potential range in still air, of course, that a glider will have. And from a glider from 1,000 feet height will travel approximately 5 nautical miles if it's a 30 to 1 glider. And of course, the better the ratio, then the further the glider will travel. When we're talking about forces acting on a sailplane, we typically refer to 3, so that's lift, drag and weight, but under some circumstances there is a 4th, and that is thrust. So when the glider is under power, it has an additional force acting on it, and that might apply when perhaps we're on an aerotow launch, so the thrust is provided by a tow plane. It might be a winch launch where the thrust is supplied by a winch via a cable, or indeed the glider could have its own power source, a self-launching glider, for instance, or a self-sustainer where it has its own built-in power source. And in that case, we then have four forces acting on the sailplane: thrust, lift, weight, and drag. And in the diagram we see here, thrust and drag balance each other out, and lift and weight balance each other out. So the aircraft will travel in at the same height in a straight line at a constant speed. If it's accelerating or decelerating, then a different set of rules applies. Now let's talk about the center of pressure. The center of pressure is the point through which the total reaction is called to act, and it's called the center of pressure. And the center of gravity is the point through which the weight acts, if you like, the balance point. So if we were to hold the object up at that point, it would be equally balanced. It wouldn't tip forwards or backwards. The problem that we have here is that as we change the angle of attack, so the center of pressure actually moves. And if we increase the angle of attack, the center of pressure moves forward as per this diagram, and if we decrease the angle of attack, then the center of pressure moves back. And this can give us a problem, because if we increase the angle of attack, the nose of the aircraft will tend to pitch up, which will further increase the angle of attack, and the pitch up will continue. And so the wing is inherently unstable, and perhaps better shown on this diagram. Unless the total reaction and the weight are exactly balanced, so they're acting through exactly the same point, then the wing will either tip up or tip down, and it will tend to tumble. So it needs to be totally in balance for it for this tumbling not to happen. Hence, we have a tailplane. Now, the tailplane is there and has three basic functions. One is to provide a balancing force for changes in central gravity, which we'll talk about in a minute. It has the purpose of dealing with the inherent instability of the main wing itself, and it's also a source of control for the pilot. And the pilot can now raise or lower the nose because he has a tailplane. If you look at balance first, the pilot's weight and all of his equipment affect the position of the center of gravity. If those loads are light, then the center of gravity will be further back. If they're heavier, on the other hand, then the center of gravity will move forward. So the center of gravity itself moves within limits between a maximum forward position and a maximum aft position. The elevator is used to correct for this, and if we're outside of those limits, well, that's what the placard is for. So if you're greater than the maximum weight or less than the minimum weight, then you will be outside of the limits for the aircraft. Stability, on the other hand, is dealt with by the tailplane in the following way. If the angle of attack is increased, the center of pressure moves forward, and there's a further pitch up action from the center of pressure moving. But the tailplane angle of attack is also increased, and that in turn applies an upward force on the tailplane, which tends to pitch the nose back down again. And this places the stability in the system. So the glider will be stable if the effect of the tailplane is greater than the effect of the wing. The size of the tailplane is to a large degree dictated by the length of the fuselage. So the further away the tailplane is from the main wing, the smaller the tailplane needs to be. This is called the moment arm. So small force over a large distance, or a larger force over a smaller distance. And that's it. So the forces in equilibrium we've looked at, glide angles briefly, the centre of pressure movement, how that moves towards the front of the aircraft when we increase the angle of attack, and therefore the inherent instability of the wing itself, and how the tailplane deals with that problem. So that's that for this section. I'll see you in the next section. Bye now.